Hello. So we continue with section 4.1. So we saw how to show a given set is a vector space or not. Now we talk about the subspace of a vector space. Now you have already heard about subspaces, but in terms of subspaces of Rn, like subspace of R2 or subspace of R3 and so on. Now we are going to talk about a general vector space. So subspace of a general vector space. The definition is very similar. So it says a subspace of a vector space V is a subset H of V that has three properties. First is that the zero of the subspace, the vector space V, must be in H, must be in that set that we are thinking of is a subspace. H is closed under vector addition. What does that mean? That for each u, v, for any two vectors in H, the sum must be in H. And H is closed under scalar multiplication. Again, that means that for any vector u in H and any scalar, the vector c times u must be in H. So this is how we are going to show that the H is a subspace of V. Now these two, B and C, they can be combined, and instead of showing separately that, sometimes we show that AU plus BV is in H. Then it conveys the same meaning, that the addition and scalar multiplication are satisfied or are closed when in H. So there is a theorem from section 2.8 that if we have a set of vectors v1 up to vk, and all these vectors are in V, then span of h1, v1, v2, vk is a subspace of V. Now this will be a subset of V. This will be a subset of V, but not only just subset, it is a subspace of V. Okay, so let's prove it. Proof. Now first thing, so we are saying that H, we are proving this H equal to span of V1, V2 to Vk is a subspace. This is what we are going to prove. So I have to prove those three conditions. So the first, we have to know what type of elements are going to be in this H. So H consists of, you can write here, H consists of, or elements of H are, so it consists of linear combinations of V1, V2 to Vk. So every set in H can be written as a linear combination of the vectors in the span of that set. So first, 0, we claim that 0 vector is in H. Now again, remember, this is not our usual 0, this one, something like that, but it is can be any 0, any type of 0, which whatever the space is. So 0 is in H. Why? Because 0 can be written as, so 0 is equal to 0 V1 plus 0 V2 plus 0 V3 plus so on plus 0 Vk. So I have written 0 as a linear combination of V1 up to Vk. Therefore, 0 is in H. Second, let V vector equals A1 V1 plus A2 V2 plus A3 V3 plus dot 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 plus A K V K, and E U is equal to V1 V1 plus B2 B2. So this is another linear combination. Then V plus A. Let me put this over here. So V vector plus U vector will be, so you see A1 V1 plus B1 V1. So A1 plus B1 V1 plus same A2 plus B2. This is V2 plus dot dot dot. Now A1 B1 A2 A1 A2 A3 up to AK, and B1 B2 B3 up to BK. They are all our scalars. So the sum of two numbers is a number. So the A1 B1 comma A2 B2 plus B2 comma dot 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 AK plus BK are scalars. Therefore, V plus U is in H. In the same way, you should be able to see that let C be a constant, or then CV will be equal to CA1B plus CA2V plus 2 plus CA3V2 3 plus dot 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 plus CAKVK. So this is NH, because CA1, CA1, CA2 up to so on, CAK are all scalars. So this is, hence H is a subspace of V. So this is our proof. Okay, let's look at the next example. This says that WB equal to the vectors in R2 such that x times y is greater than or equal to 0. Is W a vector space? So remember, x, y means we have numbers like this on the, it's our plane, it's Cartesian plane, you can think of. It may not be the Cartesian plane, but like an example is this is R2. So actually you can even draw it as, this vector space we can see as in a graph. So all the xy's, so in other words xy, you can think of it as a point, all the points which such that when you multiply the coordinates, you get a number which is greater than 0. In other words, you get a positive number. This means that x and y must have the same sign, because positive time positive is positive, negative time negative is positive. So we should be able to see that we are talking about this region, this one and this. So we can either have both positive components or both negative components. So do you think it is true? Now if you take a number or a vector here and a vector over there, and you add them, will they be always be in one of these places? Well, you can check. If I take -1, -5, and I take the other one as 5, 7, I get 4, 2. So this will be in there. But what about this will be -3, and this cannot happen because this is not in the space, so we cannot take this something that one component is negative and the other is positive. We cannot take those type of values or vectors. So either both are negative, like in the first one, or both are positive. So if I add 2 negative and 2 negative here, we get a vector in which both components are negative. So this one is in V, is in W. So does that mean all examples? Can you find something different? Well, let's try. Simple 2, 2. So you see this gives us 1, -3, not in W. So W is not a vector space. Okay, let's look at this next one. So this says consider vectors of the form S, again from the R2. So S is basically a subset of R2. Define the addition and multiplication as given. So if you look at the addition, so one vector is x1, y1, so there is x2, y2. So if we add them, this is saying under this addition we get that, but this is the same as our standard addition. So this is here, this addition is equal to just addition. So which is the same. So this is standard addition. But when we look at the scalar multiplication, so c multiplied by xy is going to give us cy cx. The standard will give you cx cy. So this is not standard. Okay, so let's see. Now if we have to check that if whether it is a vector space or not, well, we have to show those 10 axioms. But here, since, and I explained in class that the first 5 axioms are related to the additions of the vectors and or the addition operation, and the last 5 are for the scalar multiplication. So we will not do this first 5. We have since, so this is your solution. Since the addition is standard addition, the first 5 axioms are satisfied. So we start with the 6th axiom. So 6th axiom is that we are going to check if c times xy is equal to is in the vector. So first c, let c times xy is equal to cy cx. Well, this is in S. Why? Because cy and cx both are. So the reason is because cx and cy are in R. They should be real numbers. 7th. Seventh is C plus D times xy, C xy is equal to, we have to show that this is equal to C xy C dot circle multiplication circle dot xy C dot xy plus D dot xy is the same as what I have left hand side. From left hand side, what do I get? I get C plus D times y and C plus D times x. On the right hand side, we get Cy Cx plus dy dx. Now addition is the usual, so we get Cy plus Cd and then Cy plus dy. And then over here, Cx plus dx. And we are getting the same thing here because now we can either distribute this or factor out the y from the second other one, because this also gives us Cy plus dy and Cx plus dx. So yes, this is satisfied. This is satisfied. 8 is C into V into C into dV for CD and XY. So we want to show this C dot dV is the same as CD dot V. Well, this one also should be this type of multiplication. So C xy is equal to what? What do we get from here? We have C here multiplication. Now this multiplication here gives us dy and dx. And when I multiply with C, what will happen now? Can you see it will be reversed? So now we have C this is what we have. Now we want to see if the right hand side is the same. So the right hand side is CD multiplied with xy. What will this give me? Give me CD y and CD x. They are not the same. Therefore, S is not a vector space. The next one example says let W be the set of all vectors of the form 1 here. Show that W is a subspace of R4. Now, if you recall, this is actually, we have seen this type of problems before. And this type of vector, you come across this type of vector when we are solving simultaneous linear equation or a system of linear equations. And if we get free variables in our solution, then we end up getting a solution like this here. So you know that this type of vector can be thought of as 2. You can think of it as 2s, 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 0 plus 4t, 0, negative 3t, 5t. It can then be thought of as s times 2, 2, 2, 0 plus t times 4, 0, negative 3, 5. Okay, so these are the, so the W has these type of vectors. So we can basically just show that the 0 vector is in there and the sum of two such vectors and then the scalar product of such vectors. Now what this is the linear combination of this vector 2, 2, 2, 0 vector and the vector 4, 0, negative 3, 5. So any vector can be written as this. So number 1, 0. So can we write 0 like this? Yes. Then we have s is 0 and t is 0. So 0 is in W. Now let's look at and t, any this type of vector. Okay, if I give them a name, like this is, let's say v1, this is v2, then we can say SV1 plus STV2 is also in W. So this shows that hence W is a subspace